exponential. So let x be an exponential with parameter lambda, and we know that then x is bigger than 0, and it is continuous, so bigger than or bigger than equal, it isn't neither here nor there. Alright, so what do I want to do first? Method 1, proof of the memoryless property. Let's do the CDF one. So first let's write down what is meant by what is the CDF for the exponential. So it's property x is less than or equal to a, and that is equal to something that you've proved before. If you haven't proved it before, it's in textbooks. Okay, there you go. That's what we have. Right. Let's do it. Left hand side. So that's probability of x bigger than, well, just in case there's people just watching this video without watching the proof for the last one, the geometric. Let me just kind of do this quickly again. So the left hand side is s plus t, and x is bigger than the numerator part over t over probability x is bigger than t. Okay, which is equal, saying that x is bigger than s plus t and x is bigger than t is the same as probability x is bigger than s plus t. A reason I gave more detail in the video for the memoryless property of the geometric of the probability that x is bigger than t. So this is what we want. Star. Okay, now top bit. Probability x is bigger than s plus t using the CDF is the same as saying 1 minus f of s plus t, i.e. 1 minus, because people are not comfortable, sometimes students are more comfortable with this terminology. X is less than or equal to s plus t, right? That's the same as f of s plus t here. Okay. If you're wondering where that came from still, just know that probability of a is equal to 1 minus probability of not a. Right, that's what I'm doing, opposites. X is bigger than that, x is less than that. Less than or equal to, I don't want to confuse you, so it's continuous, it doesn't really matter where I put less than or equal to, let's just put less than. Alright, okay, so I can substitute now straight into that here. So it's 1 minus e to the minus lambda s plus t, which is equal to e to the minus lambda s plus t. Call this 1. So that's the top bit evaluated. The second bit, you can just look at the pattern and see it's the same. Look, this is bigger than a number. It's going to be e to the minus lambda and that number. So therefore the bottom part is x bigger than, probability x is bigger than t is just going to say e to the minus lambda t, 2. Okay, so this is like 1 over 2 in my notation. So we just say, so 1 over 2 divided by 2 is equal to that divided by that. You can see we're just going to be left with e to the minus lambda s. Okay, let's call this 3. And now we've got to look to, so that's the left hand side dealt with. Now the right hand side of the memoryless property, we want probability that x is bigger than s. But we don't have to do anything because it's just going to be, it's off this form, so it's e to the minus lambda s. Let's call it 4. Now 3 equals 4. At the left hand side, this whole thing is the left hand side, is 3. This is the right hand side of the memoryless property. So in other words, the memoryless property holds. So we're done. Method 2 for the memoryless property of an exponential, we're using the probability density function. So x is exponential parameter lambda. We have the probability density function f of x, which is continuous, is lambda e to the minus lambda x. Okay, for x is bigger than 0. Bigger than or equal to 0. It doesn't matter because x is continuous. Okay, similar, same thing as before. The left hand side now we can just say is probability of x bigger than s plus t divided by probability that x is bigger than t. And so we'll look at each of these guys. So first, probability that x is bigger than s plus t is equal to, I want to integrate this PDF with respect to x of x from s plus t. Where's the upper limit? Well, it says it's bigger than 0 can be, so it hasn't got an upper limit, it's infinity. So that's what we want to calculate. Substitute this thing and calculate this integral, s plus t. Okay, so put this into here. You can see lambda comes out, e to the minus lambda x dx. At this point I know it involves integration, so I slow down because people are often fearful of it. So let's do it. Lambda is a constant. And then we have, recall the rule, integrate e to the ax dx is equal to 1 over a e to the ax plus a constant of integration. So what we have here is minus 1 over lambda e to the minus lambda x infinity s plus t, which is equal to, I take this is a constant, so it actually come out there, so you can see lambda's cancelled, we've got a minus sign, so let's put the minus, the big brackets, and then we substitute each of these guys in. Now, because infinity, I know for stats, you probably find if it's a first stats course, just substitute x for infinity, but since infinity is not a real number, we should be taking limits. It's the limit, say, of r tending to infinity of e to the minus r lambda, and minus, and then substitute this into there, minus e to the minus lambda s plus to the t. That's what we want. But in the limit as r tends to infinity, okay, e to the minus infinity, that's going to obviously tend to 0. Tend to 0, isn't it? Or since I've written it with a limit there, I should put equal to 0. That limit is 0. Minus and a minus, that's e to the minus lambda s plus t. That, okay? And similarly, for the bottom part, similarly, you can just see directly that x bigger than t is going to be e to the minus lambda t. So again, just saying that the left hand side then is 1 divided by 2 e to the minus lambda s. Okay, and the right hand side doesn't require any more working. Essentially we're done. It is probability that x is bigger than s. It takes this form, so it's e to the minus lambda s. These two are the same. Hence left hand side equals the right hand side. Left hand side of the memoryless property equals right hand side of the memoryless property, and which will be remembered what these things are, and we are done. Okay, so we've done 4 proofs for memoryless property for geometric and exponential. Just to recap, for the discrete, among the discrete random variables, it's only the geometric distribution has this memoryless property, and of the continuous random variables, only the exponential distribution has this property. For each we've done 2 proofs, one method using the CDF and the second method using PDF for continuous case, or PMF for the discrete case. Alright, so there you go, and if you pardon the pun, let's hope that you remember some of this. Okay, take care.